Hello and welcome. In this video, we are going to clearly understand one of the most important results in the lattice theory, the characterization of the modular lattices using Pentagon Lattice in 5. We'll begin from the very basics and what lattice is, what modularity means, and what this famous Pentagon lattice look like. Then step by step, we'll walk through the statement and the full proof of the theorem in a clear and simple manner. If you have seen this theorem in your university notes textbook and found it confusing, don't worry. By the end of this video, the entire concept and the proof will be crystal clear. And after watching, I encourage you to go back and review your notes or textbook. This time you will understand everything with confidence. And yes, if you are new here, this is GVM Success Path, a channel dedicated specially for MSc Mathematics students. We make complex concepts simple and exam ready, so you can learn smarter and succeed faster. So if you are preparing for university exams, NET, or just want to strengthen your math foundation, make sure to subscribe our channel and hit the bell icon so you don't miss any updates. Let's begin. Now let's see the theorem statement. A lattice L is modular if and only if none of its sublattices is isomorphic to Pentagon lattice V54. To understand this theorem, we have to go through some basic concepts like poset, lattice, modular lattice, and so on. Let's see one by one. Now let's see what is poset. Poset is a partially ordered set. Poset is a set with rule that tells us when one element is less than or equal to another. Then it must follow three rules, that is reflexive, antisymmetric, and reflexive. Every element is less than or equal to itself. Example, A is less than or equal to A. Now, what is antisymmetric? If A is less than or equal to B and B is less than or equal to A, then A is equal to B. This is the antisymmetric property. Now, what is transitive property? If A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. Reflexive involves one element, antisymmetric property involves two elements, and transitive property involves three elements. Now, example for the poset is the set of natural numbers with less than or equal to is a poset. I hope you understand what is a poset. Now let's see what is a lattice. Lattice is a special kind of poset. In a lattice, every pair of elements has A. There is lowest upper bound and greatest lower bound. The lowest upper bound is called join. Greatest lower bound is called meet. The symbol of join is this and symbol of meet is this. For example, A join B. A meet B. Now let's see join and meet. That is, think of it like this. Join is the smallest element that is above both A and B. Meet, the biggest element that is below A and B. For example, consider all the subsets of 1 and 2 and their union is called join, intersection is called meet. Now let's see what is modular lattice. Modular lattice. A lattice is called a modular if it satisfies the following identity. For all x, y, z such that x is less than or equal to z, then x join y meet z is equal to x join y of meet z. This property is similar to that of the associative property we have studied in our high school. Now, let's see why this modular lattice is so important. The reason is it controls how join and meet interact, and modularity gives structure and symmetry. So far, we have seen poset, lattice, and modular lattice. Now, let's see what is Pentagon lattice. Now let's see what is Pentagon lattice. This is a special lattice of 5 elements arranged like a pentagon. Now let's see its structure: top, A, C, B and bottom. This is the basic structure of the Pentagon lattice. Now let's label the elements as top is 1, bottom is 0 and the middle points as A, B, C. Now the structure look like this. Here the modularity law fails. Let's see how is it fails. This is not a part of the theorem. In order to understand the theorem from basics, I have explained it clearly step by step. So don't skip the video and make the concept clear. In this structure, the element relationships are like this: 0 less than or equal to A less than or equal to 1, 0 less than or equal to B less than or equal to A comma C, then 0 less than or equal to C less than or equal to 1. The order is partial, that is A and C are not comparable, B is less than A and B is less than or equal to C. Now let's choose X is equal to B, Y is equal to C and Z is equal to A. We have chosen that Pentagon lattice to be like this to prove that the modular lattice, that is modular law, fails. So now we have B is less than or equal to A, that is X is less than or equal to Z. So first is satisfied. I hope so. Modularity law, you know that from I taught before. Now calculate for the LHS of the modularity law, that is X join Y meet Z. Now Y intersection, now for our easy understanding we say meet as intersection as we know before and meet as union, just to understand. Y intersection Z is equal to C intersection A, which is 0, since C and A are incomparable but both are above 0. Refer to the structure given here. Now X union Y intersection Z is equal to B union 0, which is equal to B. So we have left hand side as B. For RHS, first find X union Y, that is B union C, which is equal to C, since B is less than or equal to C. Then full RHS side is equal to C intersection A, which is equal to 0. So the right hand side is 0. Now you see the final results, LHS is not equal to RHS. So the modularity law fails. Therefore, the Pentagon lattice we took is not a modular. So now, so far we have seen what is a poset, what is lattice, what is modular lattice, and what is a Pentagon lattice and why the Pentagon lattice is not a modular. So far, we have seen only basics. It took about 10 minutes of time, I think so. But I'm sure, very well sure, that you are thorough in basics of this theorem. So now let's dive into the theorem. A lattice L is modular if and only if none of its sublattice is isomorphic to Pentagon lattice V45. Now, let's break the theorem into two parts. That is, if a lattice contains V5, then it is not modular. And the other part is, if a lattice is not modular, then it must have V5 somewhere inside. So, first we take a forward direction of this theorem. That is, if L contains a sublattice isomorphic to V5, then L is not modular. Now, for the forward direction, if L contains a sublattice isomorphic to V5, then L is not modular. Assume that L contains a sublattice identical in structure to the pentagon V5. Now, then pick elements A, B, C such that A less than or equal to C, and also observe the following conditions, that is A union B intersection C is equal to A union 0 is equal to A union B intersection C is equal to 1 intersection C is equal to C. We have to say this union and intersection as join and meet. To make the theorem simple, I have said as union and intersection instead of join and meet. Now clearly the modular identity law fails. That is, this violates the modular identity. Both are not equal. So any lattice containing V5 is not a modular. Now for the converse direction, if L is not modular, then it must contain V5 as a sublattice. Assume that L is not modular, so the modularity identity fails for some x, y, z belongs to L. X, y, z belongs to L with x less than or equal to z. That is, if the law fails, the identity will be like this. So now define the elements based on this failure as element U as Y intersection Z, A as X union U, B as Y, C as X union in Y intersection Z, V as X union Y. Then the set U, A, B, C, V forms a sublattice of L. So now we verify U less than or equal to A less than or equal to C less than or equal to V, and U less than or equal to B less than or equal to V. Then also meet and join operation behave like in the Pentagon lattice. So this sublattice is isomorphic to V5. Therefore, any modular lattice must contain a copy of V5 inside it. So the final statement, lattice L is modular if and only if none of its sublattice is isomorphic to Pentagon lattice V54. This is the classical structural characterization. It tells us if you are checking whether a lattice is modular, you don't need to test the identity everywhere. Instead, you just need to check whether it contains a pentagon. Now, why this theorem matters? This theorem gives a concrete and visual test for modularity. This theorem is important since this theorem gives a concrete and visual test for the modularity. Look at the shape or structure of the lattice to decide if it is modular. It is often easier to spot an V5 than check the modularity identity for all the elements. Alright, so that brings us the end of the session on the characterization of the modular lattice. We started from the very basics and understood what lattices are, what modularity means, and explored the structure of the Pentagon lattice and then saw exactly how and why the modular law fails in it. Finally, we broke down the theorem and its proof in a simple and logical way. Now that you have watched and understood the concept, I encourage you to go back to the university notes or textbook and read the formal statement and the proof again. It will now feel much more clear and easy to follow. If you found this video helpful, don't forget to like, share it with your classmates and comment below. If you have any questions or doubts, I'll be happy to help. Now, if you are new here, this is GVM Success Path, a channel created especially for MSc Mathematics students. So go ahead, subscribe now and tap the bell icon to stay updated with the upcoming lessons. Thank you for watching. Stay curious, stay confident, and keep learning.